Hi, I'm John Twist. This is the second part of our Lucas Electrical series. Today we're going to talk about generators and regulators. So we're going to take a close-in look here at a generator and see what it truly is. The first part of the generator is the field. Now I get two big windings here, round and round and round, and then the bottom round and round and round. And the electrical wires connected to it come up to the spade terminal here, and there's one wire on the inside here that goes to one set of windings, and then there's a crossover here at the back end. Oh, sure there is. I can't. Here we go. Right down here. There's the one coil connected to the other, and then the other coil is connected to ground. So the ground and the isolated connections are made up here. And this is just an electromagnet. If I am to take a wire from my battery and hook it up to the electromagnet here, see if we can do this. You can see it spark here. There's about 7 ohms here. We'll see that this you can hear this screwdriver hold on, but if I disconnect, I lose the magnetism. So we've got lines of magnetic force traveling between these poles, north and south. Then on the inside, we have a armature. This armature, in the case of an MGA or an early MGB with a generator, this has 14 segments, and every time one of these segments crosses and snaps the lines of magnetic force, it induces a little tiny bit of electricity into the windings here, and those become available. One of the brushes goes to ground, and the other brush is isolated and is available here, and this is called the D post, D for dynamo. So the electricity comes out of here and is grounded in the case. All the electricity that's being made, up to 30 amps at 12 volts, so help me out, that's what, 420 watts, is being sent out of these brushes. So there's quite a loss of energy and heat and light at these brushes, but it works. Let's take a look here at this generator here. Generators and motors are the same units. They're just constructed a little differently depending on whether it's a generator or a motor. So if I take the rear end of this guy and I hook my D terminal to the F terminal, okay, and we put it down here on the side, and I take a lead off the battery and put it to ground, and take another lead, let's bring it off the other side of the battery, and bring it to this junction here. It runs. It's an electric motor. This isn't a very efficient motor, and motors aren't very efficient generators, but this is called motoring. So a generator acts as a motor under certain circumstances, when it's energized correctly. Let's take a look at this generator, and we're going to hook our voltmeter up to him here. We get the leads from my voltmeter. We're going to put our negative here and our positive here, and we're going to energize the field. So we've got one connector to the ground and one to the field here. You can see him spark, so we know he's hot. Now you're going to take a look at this voltmeter here as I spin. Oh, we're on reverse voltage here, so let me hook this up the other way. And each time, this is set on a 0 to 16 scale, so we're getting I mean, we're only getting maybe a volt out of this at the most. But each time one of those magnetic lines of force is interrupted, then it puts electricity out the dynamo lead. So it's making just a little bit of electricity here. I want to show you now on the board how this all works together and how the generator is able to recharge the battery. So let's take a look and see how the generator works. Let's take the simplest of all electrical circuits, and let's have a light bulb here, and one side of it goes to ground, and the other side of it goes to our generator. There's armature in there, and we've got permanent magnets here on the side, and the generator is spun by your front wheel on your bicycle, and as you pedal, it starts to make electricity. It's using the permanent magnets, just like I showed you with the electromagnets. It's making electricity, and the faster you go, the brighter the bulb gets, right? That's the old-fashioned bicycle generator. Well, let's say that we don't want to run a battery or a light bulb here. Let's say that we want to run a battery. So let's put a battery here. Our 12-volt storage battery. Okay. Now, as long as we're pedaling and we're making a little more voltage than the battery, and remember that a 12-volt battery is really 13.2, so as long as we're making 13.2, as long as we're making above 13.2, the electricity is going to come into the battery, down in the ground, back up into here. Going to complete the cycle, and a little bit of electricity will trickle back into our battery and charge our battery. Remember, the battery is 80 amp hours, and we've just used it for something, and it's depressed. It needs a little bit of energy into it. Well, this is fine until you stop pedaling. What happens when you stop pedaling? Remember these windings here, okay, and these brushes? Well, these windings turn red hot, and then all the smoke comes out, and then the whole generator fries, and then all your wiring fries, and your car catches on fire. 2 or 3 of you who are watching this will painfully remember the time your car did that. So we cannot have the generator hooked to the battery if we're ever going to stop the generator. We have to put in a switch. Let me draw that. So we didn't burn up a lot of time watching me in my crummy artistic methods attempting to draw this. I've already got it up on the board. So remember, we've got our generator. Here's our generator down here, and he's still got permanent magnets. Okay, and he's spinning. And as he spins, electricity comes up into the chassis of our voltage regulator, or really it's called a control box. And there's a bobbin here, an electromagnet, just a relay. And when the voltage gets high enough, the switch closes, and our electricity now, I'm run out of colors here, our electricity comes up here, back down here, through the switch to A on the control box, and back into our battery. There's also a trickle of electricity coming through here, and through the shunt. They're called shunts in British, or the bobbin. We'll show you what it looks like on the unit. And this is great. So we spin the thing up, it starts running. If the voltage falls, if we start to slow down, and we're no longer making over 13.2 volts, this thing is designed to open back up again. So it quits charging. Hey, how cool is that? And this is called the cutout. This is the cutout. This is the first and most elementary form of protection that's afforded to the generator. Even in the earliest systems, there was a cutout. All right, now we've got a battery here, which, what did I say, had 3,000 BTUs of energy in it, and a generator down here, and a set of points. Well, if we run this thing real close to our 13.2, which is a function of RPM, and we're hovering right in that area, these points are going to open and close and open and close and open and close, open and close. That's no good. We're going to have a lot of sparking, and we're going to chow those points up really quickly. So we're going to put a little extra winding here, which we're going to show with yet another set of coils here, so that when the electricity is going through here, when this little switch is closed and the electricity is coming down through, it increases the magnetism and holds the magnetism much more firmly, holds this relay closed until the generator slows down so far that the electricity starts to back up, and then you've got a magnetic force in the opposite direction of this one, and the points fling open again. This is all designed to make the points close once and open once, not to chatter at idle. Okay? So this is the cutout. This is the right-hand bobbin inside your RB106 control box. But the problem with this, now we've got permanent magnets, and if we were going to run a car, an engine, something at a certain speed all the time, it would make no difference. But look, I mean, we run from 600 RPM all the way up through, what, 6,000 RPM. So we have to change the magnetic lines here, the magnetic force. So we're going to put some windings in here. And those are the windings that I showed you before. Okay, so one goes to Earth, and one's here, and this travels over to this side. And we come up here to our terminal F. F is for field. D is for dynamo. Here's field, and we come up here, and we have a set of points here that are normally closed, and we've got another shunt, another bobbin up here. Now I got to loop this so it looks kind of crummy here, but this comes over to Earth also. Okay, so we've got two bobbins now, this bobbin and this bobbin. These points are normally closed. So what happens? Let's say that we're not charging, the whole system is sitting still. Our cutout is open, and we start to turn the generator. Now inside the generator there's a residual amount of magnetism, hardly anything. But if you just spin this thing up to engine speed, if you put a voltmeter on your car and you're watching it without the control box in place, you'll see that out the dynamo you're getting around 2 volts. Okay, not very much, just about 2 volts. Well, that 2 volts comes up through the dynamo, comes through the normally closed switch, down into the field, and increases the magnetism. Now we get 4 volts coming out of here, 4 volts, and that comes around and increases the magnetism. And now we got 8. It isn't linear, it's not like that, but for my example this is good. 8, okay, it comes over here, it starts to climb up towards 16. It's around somewhere around 14 volts, 12 volts, 14 volts. This guy closes, and now we start charging, but we don't want to charge any more than about 14 volts, so this is designed to open. This guy opens, right? Normally closed. This switch is normally open. This switch is normally closed. He opens, and the charging stops. Well, back to our 2 volts. And again, we cycle through 2 to 4 to 8 we get up to about 14. This is still holding closed because this is happening so quickly. But these points up here end up vibrating about 60 times a second. Okay? So what happens to points when they're vibrating? Well, then they get chowed up. So rather than put a condenser in this, which could, but it's not anywhere nearly as effective, we're going to put a resistor across the points. So there's always some electricity coming through here. So now the points won't spark. We're almost done. Let's have our normally open points open. On the cutout, we start turning our generator. We get our 2 volts up to 4, going the wrong way, up to 4, to 8, start to approach 14, 16 volts or so. This guy closes, so this charging starts. This guy starts vibrating back and forth and stabilizes the voltage by stabilizing the magnetic lines down here, and we end up with a charging rate of around 14 volts. So we got 14 volts going into our battery. But what happens if the battery's dead? I mean, like dead. And it's really, I mean, the generator can really work overtime, and it'll burn it out. It'll get it so hot it'll fling the solder out of the inside of the generator. So here we are going to put an extra set of windings here, and we're going to make this A, and screw this up here a little bit, and this we're going to come down and make it A1. So we've got another couple of loops here, so that if we're drawing too much current out of the generator, it adds a little more magnetism and holds these points open a little bit longer, which reduces the charging rate. So this extra set of windings here is an attempt at current regulation. Let me take a control box. We're going to come in here closely now, and let me show you the control box. So here he is. Let's take a look at him here. I've tried, I've got my A and my A1 mixed up. This is so embarrassing. Here I am trying to show you how all this stuff works, and I get my nomenclature wrong here. A, and that goes to our battery, and then A1 is our extra lead out the top, and A1 goes to the car, runs the headlights, so forth. All right, so we've got A1, A, field, dynamo, and earth. Let's take this guy and look upside down. I've got to grab myself just a little screwdriver here so I can point. So here's our earth terminal. Remember, connected to the earth terminal are the two ends see these 2 wires here. These are the 2 wires from the bobbins. Okay, right there. Look at that. How cool is that? Right. Here's the 2 wires. Our next one over is D, and that's common with the chassis. And here's the resistor that runs between D and F. Here's F. Here's D, and here's the resistor that goes between them. And then these are the straps that go to A and A1. Let's pop the top apart here. Here's the cutout. Okay. So when we come up to charging voltage, this guy shuts down and makes contact with the points, and the electricity that's being charged then, this big winding around the outside, that's this winding that's common with the normally open switch. This is the normally open switch. This switch closes. You can see the little tab of copper here, and this is one of the 2 pieces, and this shuts down. Okay. Over here on the other side is our normally closed regulator, and when this pulls open, these points right inside of here, these open up. Okay? And here's our attempt at current regulation with a couple of windings around here, and one of these, the back one, goes to A, and the extra half loop on top goes to A1. So again, to polarize it, jump between A and F. Okay? A penny, a screwdriver, a paper clip, whatever you can find. Just jump across it. Sometimes these are hidden, it's hard to get to them, and so forth. So again, all you need to do is take a hot wire and pull the wire off off F, and flash the wire against F field. And that will magnetize the generator and give it its initial magnetism. And from there on, the car will make electricity in the conformity with whatever ground it is. So, I've tried to show you about the generator. Generators and motors are much the same. Generators designed to make electricity. These guys will make about 30 amps, 12, 14 volts. It's going to be 350 watts or so, about half a horsepower. And it's made up of the field. Fields once in a blue moon go bad. It's made up of the armature and the brushes. The brushes are carbon and they wear out. The armatures get crummy, blow their solder out, short out, and it stops making it. Sometimes the control box itself goes bad. Sometimes both things go bad. And if you're checking, you're just doing a field test, okay? You're just doing a field test, and you want to know, your red ignition light stays on. It's like, oh boy, why is it staying on? Pull the two wires off the back of the generator and take a lead like this and hook one to the field, and with this guy spinning at, 1500 RPM, touch the other terminal and break it. It's either going to be no spark or it's going to be at the 4th of July. And you want a nice big flashy spark. That means that the generator's good. If you get a nice big flashy spark, the generator's good, the control box is bad. If you don't get a nice big flashy spark, you know that this guy's bad, and this guy might be bad too. You don't know until you put it back together and see. Our next installment will be about the alternators, which are far simpler units and less cumbersome, easier to make, lighter weight, make electricity at lower RPM. Oh boy. But for anybody with a car up through 1967, in the MGBs anyway, it came with a generator, it should stay with a generator. Hey, until later, safety fast.